Okay, in this next module, 5A, we're going to get started looking at what's called linear regression models. We're going to talk about what the purpose of regression is and how to do an estimate of a linear regression. In this case, we're only going to look at linear regressions with a single so-called predictor or independent variable. And we're going to talk about assumptions underlying the regression model and also take a look at how to use ISLE for doing linear regression. Here are a couple of examples of linear regression plots. You've probably seen plots like these. You may have done regression yourself in the past. In this left-hand plot, we're showing the size of homes in square footage, and as a function of size, we're showing the price of the home. Now, there's not a definite one-to-one match between the price of a home and the square footage of the home, but there is a linear-ish relationship. As the size of the house goes up, the price of the house also goes up, although there is a lot of scatter around that line. Similarly, here we're looking at years of employment with salary as a function of years of employment. Now, when people first get hired, they're given some initial salary, and at this company at least, it appears that the longer people remain with the company, on average, the higher their salary becomes. Now, that, that we don't know the cause. That might or might not be because the company is kind to its employees and gives them more money over time. That might be a part of it. More likely, the years of employment reflect, I mean, the more years of employment you have, presumably the more experience and knowledge you have, and the more productive you are, and the higher level within the company you are functioning at, and you are therefore, on average, probably deserving of a higher salary. Of course, there's a whole question about whether your salary reflects what you deserve, but that's a different thing. Okay, so we want to model how two or more variables are related. In this module, we're only looking at how two variables are related. Later, we'll look at what's called multiple regression, where we can have multiple variables involved. Can I conclude that if I increase spending on advertising, that will increase my sales of products? Can I conclude that a proper diet lowers the risk of heart disease? Is there a relationship between, let's say, the number of vegetables you eat each day and your heart disease risk? Do employees with more experience earn higher salaries? We could approach each of these questions as a simple, a simple hypothesis test and just test for yes or no. But we would like to be able to predict the value of one variable given the other variable. So in the advertising case, if I increase advertising by 50%, what will that do to my sales? If I increase advertising by 100%, what will that do to my sales? And so forth. So given a person's demographic characteristics, which includes things like their age, their height, their weight, their gender, their employment status, their marriage status, all this other kind of stuff. How often would we expect them to utilize the particular website that we have constructed, and so on. Okay, so we're looking at linear relationships between two variables in this particular module. It's also possible to do things like modeling quadratic relationships or parabolic relationships or what have you. In a linear relationship, the dependent variable, which we're just going to call y without any cleverness, is a linear function of some other variable x. That is, there's an intercept value, and then there is some slope value times the value of x. So x is called the independent variable, y is the dependent variable, or in terms of our plots here, x is the horizontal variable, and y is the vertical variable that is some function of x. Now, it's also possible to use linear regression to model certain kinds of nonlinear relationships, such as an exponential relationship or a power law kind of relationship. Let me show you what the heck that means. Okay, so an exponential relationship, let's suppose that you have a portfolio of stocks, and this is your portfolio value on the vertical axis, and this is time on the horizontal axis. Well, on average, if you have a diversified portfolio, the return on your investment should be exponential. Okay? But it turns out if you take the log of the value, you can make that a linear relationship. Okay, log of value as the dependent variable with time as the independent variable. In that case, an exponential relationship should be a linear relationship. Humans are great at identifying when something is a line or not. Humans are much less great at understanding when something is exponential or parabolic or other kinds of shapes. Lines, circles, squares, these are things that it's really easy to understand. But in the case where we have a more complex relationship, if we can take the log of the dependent variable and discover then that the relationship with the independent variable is linear, that tells us that we have an exponential relationship. And we can represent an exponential relationship as a linear relationship by just taking the log of the dependent variable. Okay. There's also what are called power relationships, power laws. Here is in the slide is an example of that where the logs have already been computed. These are relationships that look sort of like this. We've got some independent variable on the horizontal axis and some dependent variable on the vertical, and the plot looks something like this. As an illustration, this might be some number of books or book titles, and this might be the number of copies sold. Well, in this first part of the graph, we've got the vast majority of authors who've written tons of books and have very limited sales. Being a writer especially a writer of like fiction, is a good way to be impoverished for the vast majority of people. I'm actually acquainted with a number of science fiction writers, most of whom have day jobs. Okay, they're teachers or professors or scientists or whatever, and they do write and publish books that don't sell very much. And then down here, in this tale, we've got Stephen King's books. We've got a tiny number of books that have enormous sales, millions and millions of copies. Now, this might look like a pretty ridiculous kind of plot to do, to handle a linear regression with. But if we take the log of both axes, log of the number of books, and the log of the number of copies, we'll find that this might very well look pretty linear. All right, and that's what's being illustrated actually on the slide here. Here we have the log of the number of incoming links to a particular blog as a function of the log of the rank of the blog. So the top-rated blog, the number one blog, which has a log of 0, has this huge number of links to it. The second most popular blog, which has a log, between 0 and 1, has many, a large factor of fewer links. Although if we take the log of the links, it's not quite so obvious that the relationship looks like a power relationship like what we have in my book diagram. Okay, and as the ranking of the blogs declines, it turns out it doesn't take you very long to get down to much less popular blogs that have, like 100 times fewer links than the much more popular blogs. And yet we can still model that as a linear relationship by taking the log of both axes. All right, that's a detail I don't want to overemphasize. But the point is, an ordinary linear relationship we can analyze using linear regression. And in special cases like exponential or power relationships, we can also use linear regression by taking logs of one or both axes. All right, so once we have a so-called best-fitting regression line, we can use it to make predictions about, in this example, the salary for somebody based on their number of years of employment. That is, what is the expected salary based on some number of years of employment? When years of experience equals 10, we expect the salary to be, and we can, just look up on this plot here. Well, 10 years of employment, the salary ought to be, looks like close to 40,000, like maybe 39,500 or something like that. We can also conclude from this that the slope of this line is positive. We can conclude from the analysis that the slope of the line is positive, and therefore salary does increase with experience. Now, the question is, how do we achieve, or how do we find this so-called best-fitting line? And what standard linear regression does is to compute the least squares of the departures from the average of all of the observation values that we have. All right, so in this plot, these blue dots represent individual observations of salaries of people as a function of the number of years of experience. And I don't think, squinting at this very closely, it doesn't appear to me that any one of these people is directly on that so-called least squares line. People will tend to be closer to the line as opposed to further away from the line, but they will be, above the line, below the line, whatever. Okay, so for this particular data point here, x sub I, y sub I, our predicted value, based on our least squares regression, is down here, and this difference between the two is referred to as the error for xi. That is, the error is what we call the difference between our linear model and the actual observation. So we want to figure out some regression line, y equals slope plus, y equals intercept plus slope times x, that minimizes the difference between the observed y's and the predicted y's. Or I should say minimizes the square of the differences between the observed y's and the predicted y's. How in the world are we going to do this? And the answer, fortunately, is not to do all kinds of computer simulation to try to, narrow in on a B0 and a B1 that in some way minimizes that value. The solution here, fortunately and unfortunately, I guess, involves calculus. Okay, so this is the hand-wavy part here. We're using calculus. We're also using linear algebra, but we won't bother mentioning that. Okay, so we've got the sum of the squared errors is the sum over all of the observations of the observed value of y minus the predicted value of y squared. So it's the sum of the squared differences, the sum of the squared errors. Now, if I take the partial derivative of that squared error with respect to the intercept, and I set that to 0, and I also take the partial derivative of the sum of squared errors with respect to the slope and set that to 0, it turns out I end up with a giant matrix of n equations and n unknowns, which I can then solve. And that solution tells me that I can minimize the sum of the squared errors by estimating the slope as the sum of the squares ss sub xy, which is the sum of, it's not squares actually, it's the sum of the differences in x from the mean times the differences in y's from the mean for each xi and corresponding yi, divided by the sum of the squares of the differences just for the x's. And then the intercept term is the mean of all the y values minus the slope that we've computed times the mean of the x values. Now, this may or may not mean anything to you. Well, let me jot down these equations to be more clearly. So we compute x bar which is simply the sum of the x sub i's divided by n. And we compute y bar, which is simply the sum of the y sub i's over n. We also compute the sum of the squares of x with x. I don't like this notation, but whatever. People use it. This is the sum of xi minus x bar squared, and then the ss of xy is the sum of xi minus x bar times yi minus y bar. And from those four computed values, I can calculate the estimate of the slope, and I can then calculate the estimate of the intercept. Now, another way of expressing the slope, which I'm not going to derive or justify, but you can also think of the slope as being the covariance of the x and y divided by the variance of the x. And this is the equation that I prefer. I find that easier to remember, and I find it. Well, of course, it assumes that you're happy remembering that the covariance of x and y is this value over n, and the variance of this is. I'm sorry. The covariance is this over n, and the variance is this over n. But since you're dividing by n in both places, the n's disappear and you have covariance over variance. What good does that do you? Well, let me draw a plot. Here is some relationship. And these are my, this is my independent variable, which is x, and this is my dependent, which is y. And just eyeballing this, let's suppose that the least squares line is there. If I remember that the slope of this thing is the covariance of x and y divided by the variance of x, well, the variance of x is a measure of how spread out the x are. And if the x are less spread out, that is, if the x values for your sample are in a tighter range, I hope it's intuitively clear to you that that means that the slope of this is going to have to increase. Okay, so in other words, if the x's are tighter together, the slope is going to rise. On the other hand, the covariance has to do with how y varies with x. If this covariance is large, that means that y depends very heavily on x, and also the slope is going to rise. But if the covariance between x and y is low, then the slope will become shallower. Okay, so your mileage may vary, as people sometimes say. I find this formulation, covariance over the variance, to be a more intuitive way to think about the slope. But you can just, do the computation and get the answer, and obviously it works. Okay, so here's a particular example. We've got only 4 observations in our data set, which is fairly pathetic. Here's the plot in the lower right corner of those 4 examples. Employee 1 is making $40K after 5 years. Employee 2 makes $30K. Employee 3 makes $35K. Both of these are after just 1 year. And employee 4 is making $45K after 9 years. So if we plot those red dots, we can then compute our mean of X, our mean of Y, our SSXX and SSXY, and just run out the computations, and we get that the slope, the change in salary per year, is $1,591, and the intercept, which in this case we can sort of think of as the typical starting salary, is $31,136. Now, there are important assumptions built into this linear regression model. First of all, we're assuming that the relationship between the dependent variable and independent variable is approximately a linear equation. You don't want to attempt to apply linear regression in situations where that's clearly not the case. Like, you would not want to do a linear regression of the vertical height of a baseball versus seconds of elapsed time as that baseball, that baseball has been thrown and it's going through the air. We know, even if you've only had 10 minutes of physics at some point in your life, we know that that baseball is not going to go in a straight line. That baseball is going to go in an approximate parabola, although wind resistance is going to tinker with that being a perfect parabola. So it would be, it would be dumb to apply a linear regression model to something like that. But for the case of salary versus years of employment, there is reason to expect that there is some linear relationship between the two, although it may not be perfect. Okay? And in fact, it's definitely not perfect. Not all people's salaries are going to be exactly on that line as a function of years of employment, because it's also going to depend on your training, your efficiency, your productivity. It's going to depend, unfortunately, on how much your boss likes you. It's going to depend on your negotiating skills. So there are a whole bunch of factors involved here. We also have an assumption about the errors, which remember is the differences between the observed values and the predicted values. We assume that these errors are independent and follow. Come on, mouse. You can do it. I promise. Come on. Doesn't want to do it. That the errors are independent of each other, and that furthermore the errors are distributed normally with a mean of 0 and some, although we didn't bother to compute it in what we've done so far, some standard deviation. Okay, that is around this line, we assume for every year of employment that there is a normal distribution that the errors are drawn from. And that may or may not be a great assumption. The requirement of the independence assumption gives us that the probability of a given error value for a given independent value of X is not dependent on X. That is, that the probability of a given error level, either positive or negative, is just independent of X. Okay. Here's another example. This time, the independent variable is the number of drinks consumed, and the dependent variable is the reaction time to some stimulus. There is both a deterministic component to this, which is indicated by the slope and the intercept. On average, people have a certain reaction time even when they have had nothing to drink. And as they have consumed more and more, reaction times tend to increase. Now, there are errors, so that not everybody has exactly the same reaction time. And the errors indicate to us that there's some other factors going on, in addition to just the number of drinks that people have. Some people have a greater tolerance or a less great tolerance to consuming alcohol. It's known that your weight will affect how the number of drinks affects your reaction time. On average, heavier people are more tolerant than less heavy people to a given number of drinks, etc. Let's take a look at some aisle output. Okay, this is basically showing the plot produced by aisle. So I'm going to do this aisle regression demo for our salary. All right, so here's our salary data set. We have got 46 observations in this data set. And the first column tells us the person's salary. The second column tells us the number of years of employment. To get my linear regression, I show my toolbox. And regression is under models. So I'm going to choose a simple linear regression. And by default, it automatically comes up with salary as my dependent variable and years of employment as my independent variable. I'm not going to subdivide this into different groups. I am going to omit missing values, and I will generate the linear regression, and poof, we get out the same table that we got over here. And basically, in this coefficient column is where we can read our intercept term and our slope term. Okay, so according to the model, salary is related to years of experience as 28,394 with 0 years of employment, and that plus 1,007 times the number of years of experience for more experience. Okay? So we've now taken a look at how to estimate these coefficients, the intercept term and the slope term. We haven't yet talked about whether these estimates are any good. And that is something that we will get to in the next module next week.